There we go. So we'll start by taking your guys' questions on variation, minus the extra credit one, obviously. But what questions do you guys have from the variation homework? Measuring variation. Remind me again why we care. Why do we care about variation? Why wasn't center good? I'm sorry, Jenny. Why do we just care about center? Center was so awesome and easy to understand. And then you gotta make it all confusing by talking about variation. Why do we care about that? Go ahead, Elena.
Because world is not perfect, unfortunately.
Oh, good. It's not uniform, right? You've got this.
There are some deviations.
Boom! You've got to be. No, wait a minute. I was sitting on the way back from my East Coast trip. I bumped in next to a cattle. Wait a minute. What the hell did he say his job was? He creates. Okay. He impregnates cows and then freezes their embryos, and then he's like genetically modifying beef cows to try to optimize, and I had to kind of choke back my hippiness on that one, but it was interesting hearing him talk about it. When I left that go, and we talked about like how he does his job, like, well, how do you know whether or not what you're proposing is going to create a better, say, beef cow? He's like, well, I got to look at data sets. I'm like, really? Tell me more. We started chit-chatting, and he said, well, you can have this data set where you've got 2 or 3 deviants that drive the average with the chart. And I'm like, oh, that is wonderful. So that's why we care. Not so much the cow thing, but like that's why we care, because the world does not behave uniformly. It behaves with variation, and sometimes the variations that are excessive can have undesired effects on measures of center. So if you can figure out a way to classify the variation, hence this entire talk, then we get there. So this is so interesting. Guy from Montana, flying around the country, checking out cows. And it was so funny hearing what he had to say too. He said, like, I went to this one farm, and the guy said, my cows aren't producing. He was like, well, what are you feeding them? He's like, feeding them. I'm like, yes, what are you feeding them? He's like, I don't know, they run around here and eat whatever's on the ground. And he turned around and it's almost like dust. He's like, the reason they're not producing might be because they're hungry. Maybe. And he's like, and the guy was like, oh, really? Exactly. That's what I was like. I'm like, that's not a bitch. Take it away from him.
Well, sometimes they're too fat. Like
well, this was not that case. It was the other side of the coin. So what questions do you guys have on variation? I didn't include any cow problems in your homework set. I apologize. But I figured you knew about cow problems.
The spreadsheet. Can you please show me finally?
Oh, that's right. There is one with the spreadsheet. Yes. Let's fire that one up.
I was trying to play with it for 2 days. I'm sorry.
No. Let's do it all. Let's take a look at it. Let's take a look at it. This was a question I used to have on exams, and I realized that it's not a good place for. It's not a good exam question. So let me get to this sheet first. There we go. All right, we're in variability. Which one is that, Elena? Do you remember?
It was actually E7.
E7, okay. Here we go. So it kind of, E6 and E7 are kind of together. We'll pop this guy open at first. And E6 actually relates to what you guys were just mentioning. You're taking 10 consumers' ages at random. And their ages are all between 17 and 81. So 17 is the youngest they could be, 81 is the oldest they could be. Suppose the sample consists of 10 consumers that are all 23 years old. Their average age is 23 years. What would the standard deviation of that sample be?
0. Because they're all 23 years old.
There wouldn't be any variation. They're all the same. The whole measure of variation is to measure what?
How far they are from the...
Good. How far they are from average. Well, if every one of them is equal, if everyone, let that out.
I couldn't.
You couldn't go. Okay.
Yeah. It's because you talked to me, that's why.
I'm sorry, I ruined the
okay.
perfect sneeze. What's the one that's supposed to help sneezes? Bumping the nose or looking at the light? Looking at the light helps with sneeze. Bumping the nose stops it. Is that, you ever heard that one?
Yeah.
Okay. Anyway.
It's okay.
It'll come back.
Yeah.
I hope not. So, if they're all on average, if they're all at average, there is no deviation from average, therefore it's 0. Now this one, that's why I mentioned here, because it's highly unlikely that it will actually happen. I said assuming all their ages fall between 17 and 18 inclusive, what would the largest possible standard deviation be? So we got the smallest at 0, what's the largest possible? And that's where this guy here kind of helps out. Let's open this bad boy. What this was supposed to do was to give you a way to kind of explore this question graphically. So what I have here, and you don't have to use the sliders at all. The idea was you could actually change the numbers down here. The sliders just gave you a way to change the numbers, just a different way. So what's going on here is that you've got the 10 ages up here. It's a dot plot. essentially. It's a dot plot. So you've got 77, 72, looks like about 61, maybe 59, 52, and so forth and so on. And this box here kind of tells you what to do. The red box up there is the average age of the 10 values, which is down here. And this is the kind of stuff, minus the sliders, you'll be doing in your first take-home exam, like building this kind of or filling in this kind of a sheet. So basically the sliders, you see, you click on these bad boys, and you see how that one blue dot is moving to the right. This is the one thing I couldn't figure out. It's kind of counterintuitive because you're clicking down and the age is going up. I couldn't quite figure out how to turn it around the other way, so hopefully you can ignore that. So basically, what you're doing is you're making this person, this first customer, this first mall customer, now that person is 81 years of age. And I wanted you to kind of just mess with these values and try to make that number as big as you possibly could. That's all you had to do. Basically explore to see what would give you the largest possible standard deviation. So.
And it doesn't matter which one you actually...
Yeah, well, you have to kind of mess with all of them to kind of get that. Jenny, you had an idea coming. What was that idea?
No,
You didn't? You sure?
Yes.
I saw motion. Like an amphibian, I see motion. So, did anybody get a chance to play with this at all? What does your gut tell you? Where do the ages have to be in order to maximize... Jordan, what do you say? Chris, for some reason. On the outside. So tell me, there's 10 of them. Where should I be? 17? How many is 17? How many 81? 1 and 1. Okay, so let's put this guy here at 81, and let's put this one here at 17. Okay? So now the standard deviation is 23.4. Does that make sense?
Yeah.
Now, notice it went up. It wasn't like 16 or 17 point something, but then we grabbed the 17 and 81, and we set those two ages all the way to the end. The average didn't move all that much, but the standard deviation did go up by about 5 years. Why? Why did the standard deviation go up when we took those two and put them at the extreme values? Why do you think? What happened? Why did the standard average stayed about the same? What are you thinking, Haley?
Because you put them to the extremes, like you just said, and so there's going to be a wider, right, from the average.
You got it.
to the
What does
extremes.
standard deviation measure again, my friends?
The average between the average.
You got it.
Yeah.
Average used twice, right?
Yes.
It's the average distance from each data point from
The
average. So what you essentially did was you kept the other ones at roughly the same value. They didn't move at all. And the average didn't really move at all either. It stayed essentially right where it was. But you took two data points and you shoved them essentially as far as they could be away from average.
So then you keep doing it.
Keep doing it. So say for like age number 3, where should I put this guy right here, age 3?
All the way down.
All the way down? So now he's at 81.
And then all the way up the next
Now watch this guy here, friends. Why do you think he was all the way up?
Yeah.
See what's happening to those standard deviations? How about this guy here?
All the way down.
Down. Up. Okay, notice there's a little bit of fluctuation there. There was fluctuation as I was moving it because it was passing through average. And if it's moving towards the average, the standard deviation is going to be going down because it's getting closer. But then it starts pulling away. So just continue, Haley. Keep going. I like this idea. This is cool. So down, up, down, up. All right. So I got it at 33.7 right now. How do I know we're right? And this is a loaded question. And this was I don't expect a mathematical proof on this one, but I expected you to kind of goof with it a little bit. So let's take Haley and Jordan's idea, but not make it symmetric.
Okay.
So in other words, Haley and Jordan said put it at the extremes. Haley said put half at one extreme and half at the other. Suppose this last one that I put at 81, suppose I instead put that one here at 17 instead. Now what happened to the standard deviation? It actually got a little bit less, didn't it? It went down a smidge. It was at 33.7, now it's at 33. So why? If they're still at the extremes, what's the beauty of having half at one extreme and half at the other? Jordan, what are you thinking?
Because the average would be dead center instead of leaning more towards one side.
That's the key. The key is where the average is. Watch the average, that red box, as I slide this age to 18, or excuse me, to 81. Where's the average going? Aha! It's heading that way. Now some of you are going to say, yes, it's getting closer to this one, but it's getting further from these. So wait a minute, if it's getting further from those, shouldn't it cancel out? Why doesn't it cancel? And again, this is a tricky question. This is not inherently obvious. Why does the fact that it's getting further away from this What are you thinking, Anthony?
There's more on the one side.
There's only 4. There's only, Jada saw it too. There's only 4. And this is the one thing I couldn't make Excel do. It'd be nice if I could stack the data points so you could see how many there were. But now there are 4 here and 6 here. So there's more that are now closer than they were to average than were further away from average.
It's like the scale.
It's almost identical, and there's where your scale is. The sum total of those distances is greater when you have them split symmetrically like that, because your average is now directly between the 17 and the 81.
Yeah.
So there you go. That's all I wanted you to do is kind of mess.
My mistake was I was looking at the average instead of standard.
Oh, gotcha.
And second of all, instead of doing this, that, I was, okay, do you remember we were looking at we just got rid of these guys and then these guys.
Median.
So that's
You're
what I was
doing the
doing.
median. Gotcha.
So
Well, and
my
part of this class, and I try to take as much of this out as I can, is learning that lingo.
I was
I don't want it to be
close.
lingo driven, but
I
there are
was
certain
close,
terms that
but-
kind of have to get comfortable with.
Yeah, that's cool.
Fair enough?
Yeah.
Fair enough. So that's all that was. That's all that was kind of messing around with that. And hopefully, if you got a chance to look at it, maybe you started by, taking the idea of asymmetry and pulling it this way. So you say, here, let's leave 1 at 17 and the rest at 81. And you think to yourself, you still have that same range. You're still spanning the entire data set, but now the average is so close to these. One of them's not quite, no, that was an 80, but same point. Now the average is so close to here, you have 9 that are close plus 1 that's ridiculously large, but that one that's ridiculously large is tempered by the 9 that are ridiculously small. And then you can see that in your standard deviation. So it was just a mess with kind of problem. And this, honestly, it's so interesting to watch statistics education progress. This is how much statistics gets done in the world today. Like research statistics is created by setting up sheets like this and seeing what happens. I'm giving a talk on it on the Friday afternoon at my conference. We go to a math conference every year, and it's called Monte Carlo simulation. You guys will play with it in your 3rd project. It's you'll open up an Excel spreadsheet, hold down the F9 button, and data sets just behave as they behave. Like there's no preconceived notion about what they're supposed to look like a bell curve or a skewed curve. It's just like, well, here's a situation. Here's what it looks like, and then you just let it go, and you look at what happens, like you're doing here, and it feels weird. That problem-solving process probably felt weird to you guys because you're used to like x equals 2. Yes, thank you very much. I'm done. Well, what is x equal? I don't know. It's in there somewhere. Let's go track it down. Let's experiment. Let's mess with it. And this is where computers really, really come in handy because they allow us to do that without having to carry the one, freaking sharpen the pencil. I mean, it's sharpening the pencil and carrying the one for us, which is fantastic. Yeah, Lynn, go ahead. Can I shut this bad boy down? Is that
yes.
cool? Go ahead.
E9, 10.
Let's take a peek at E9 and 10.
Yes. And
Refer back to question
yes.
E1 from the previous, that is central tendency. Let's take a look at that one.
It's about.
Let's do this. Let's open a new tab. And then we'll open this one too. Okay, so here's central tendency, E1. Please look at the data set from, look at me, Mr. Recursive. Look at the data set from question 16. Oh, you know what? I don't even care what the data set is.
Yeah.
Doesn't matter to me. It's irrelevant.
When we double, everything doubles, right? So
Okay,
mean
let's,
and
so
median doubles.
in E1, if you double each data point, so I don't care what the data set actually is, whatever it is, if you make each of the points twice as big as it was before, what's going to happen to the mean and the median?
Double.
Good. Anybody have why? Why does everything double?
Because double it.
Because you double it? That's awesome. That's so much better than I was going to say. You double it. Can I be a little algebra-y on this, just a smidge? Just to kind of drive this point. Okay. So let's do this. Let's come over to here. Okay. So I'm going to use the formula only because the formula, I think, is the easiest way to look at this. So the average of a data set, as you guys know, is equal to the sum of all the data divided by how many that there are. If we double, I'm going to write one more thing if it's okay with you guys. This would be the same thing as the first data point plus the second plus whatever the nth one is, all divided by n. I'm being a little bit symbolic-y on this, but just I think it's going to help us to answer this particular question. And the n is just how many there are. Each of these would have a number attached to it, if that's fair. Okay? So what E1 is saying, suppose we double each data point. So what that means is, we're going to multiply each data point by 2. So what that's going to now look like is 2 times x1 plus 2 times x2 plus all the way down to 2 times xn, but it's still over n. You still only have n of them. Whatever n is, whether it's 5 or 10 or 17 or 150. Now, you see how each of these things is multiplied by 2? There's a property that you learned back in algebra class that allows you to pull that 2 out. And you're left with just x1, x2, up to xn all over n. Remember what that property is called? Say that again? Factoring is an example of this property. It starts with a D.
Distributed.
That's the one, Jenny. It's a distributive property. Oh, Haley, it's the one. Sorry, I heard a voice coming from that
It's
general
okay.
direction. Yes. That's a distributive property. That's what you see. You can pull the 2 out. Now check this out. Now we're going to use another property from that class, which I don't remember the name of. You've got something times something over something. I'm going to pull the 2 out and put it in front of all of this. x1 plus x2 plus xn over n. Just pull the 2 forward, if you will. What's in parentheses right there? Isn't that the same as this up here? That's the same as that. And what's that equal to? This. And what's that equal to? X bar. So it's 2 x bars, which is what the answer is. It's twice as big as the average used to be. So you can algebraically see, by doubling each data point, using a couple little cool things from algebra, you double the average as well. Kind of slick. Is that ish sense? Ish makes sense? We're getting there. Median would be the exact same argument. Median would be the exact same argument because if you think about, you actually mentioned it when you said, you're going to get to the same position halfway from 0 to n, or 1 to n. But that position, whatever it was originally, will now be twice as big as it used to be because you doubled it. So that's why the median's also doubled. Fair?
Yes.
Fair enough? Let's go back to the variation
Mine,
homework.
yes.
Because the question was on the variation homework. Now the question is, refer back to E1. If you double, slide this back over this way. If you double each of the data points like we did over here, what happens to the standard deviation?
It's bigger.
How much bigger?
Twice.
Twice as big. Why?
It's double. That's my answer.
Because all the data.
What was the S you used, Jenny?
What?
Because it's double is use
Oh,
some
I don't
kind
know.
of.
I don't know.
Oh, so I got it on camera, so we'll get it later.
Double-ated.
Well, it's double-ated.
Yeah.
It's double-ated. That's very, very good. The reason it's not we could do it using the formula for the standard deviation, but I don't want to. I don't want to. What I'd rather do is to draw a kind of general number line idea over here. So this is E9, right? E9. Okay. So here's your original data set. Original data set. And you know, it doesn't, this is going to be, it's actually not anywhere near as general as that one is, because that one doesn't have a number line or any apparent views on a number line. So what I'll try to do is I'll try to make this as general as I can. I keep saying the word general. I apologize if that's upsetting anybody. When you're trying to answer a general question, this is a very general question. It's very, very general. Now, it ties back to a specific data set, and you can answer it with that data set if you want to. And I'm trying to answer this more generally. So, in other words, what I can say is, you could go back to E1 from central tendency, which tells you to go back to or number 16, whatever it was, from central tendency, and actually put the numbers in your TI and run the numbers. But I'm trying to get you a more general solution that you don't even need numbers to do. Here she comes, here she comes. So you've got a bunch of data points, and you don't know where they are. It's going to look something like this, or ish, a couple there. Okay, and that data set has a standard deviation. It's also got an average. I don't care what they are. I don't care what they are. What we've now done is, we got the new data set. As a matter of fact, let me make life a little bit easier for us. And let's compress this down a little bit. Yeah. Let's do that. And let's put a reference point on. This will make it a little bit easier for us, I think. Yeah. I'm going to put 0 on there as a reference point, because this way we can double and actually see scale, if that's okay with you guys. So now, it's sense to put 0 in the same spot. We took every data point and made it 2 times further away than it was from 0. That's what doubling means, right? Distance from 0 is now doubled. So these 2 data points were here, they're not going to be here. These were here, they're not going to be here. This one was there, it's now going to be like over here. I erased that, I'll put it back in. That's there, it's not going to be over here. Okay? These guys were right here, they'll be shoved over a little bit. That one was here, it's not going to be twice as far away. That one was here, it'll be twice as far away. That one was here, it'll be twice as far away. So, clearly the standard deviation is more than it was before, absolutely. But since each distance, now the average is somewhere up there as well. The average is pretty close to 0. I mean, based on how I drew this thing, I drew it kind of L-shaped with 0 kind of, I placed 0 kind of, let's just say the average is here. Let's just say the average is here. Well, the average is also going to get doubled because of what we said back in E, whatever it was. But since each distance got doubled from the average, you essentially have doubled all of those distances as well. So if you doubled every single distance in the average distance, based on our argument from over here, has to also be doubled. So that's, yeah, it definitely gets bigger because it gets spread out, but it gets bigger predictably. It gets exactly double. Go ahead, Jordan.
I'm saying that there's a 0 there, and negatives multiplied by double, wouldn't it make it a positive?
No, you're thinking squaring. Squaring a negative makes it positive. Doubling just makes it twice as negative. And that's just, the reason I picked 0, Jordan, is because you have to have that reference point of 0 in order for it to actually make sense to get to double something. Yeah, you're thinking squaring versus doubling. And we had to deal with that, right? That's kind of what variation dealt with, was squaring versus just adding or summing up. Cool so far? Ish? Okay. E10 says look back at E2. Let me look at this one real quick. Let's go back. E2. Oh, if you decrease each data point by 5. Okay, beautiful, beautiful. Okay. So now, that's the same data set. Same data set. We'll start with that one. But now we're going to take each one of those points and knock it down by 5. Now, looking at the central tendency problem, if we decrease each data point by 5, what's going to happen to the average? It has to be decreased by 5 as well. Because and how about the median? It's going to decrease by 5 as well. Because computationally, we can apply the same argument we did over there, but instead of 2x plus 2x, it'll be x minus 5, x minus 5, x minus 5, and essentially you pull the minus 5s out, and the whole thing is less 5. So the same algebraic argument happens with a slightly different property, or properties. So here's E9, but E10 now, you know what, for E10, let's go right here. Because what I want to do is I want to put both data sets on the same number line, I think. I think this will make this more clear. Let's slide this back to front. There we go. All right. And then we'll do original in black and purple for new. So here's E10. And again, you got the original data set. Do that black. And ish looked like that. Whatever it looks like. Blah, 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 blah. So now we're going to take each one of those and knock it down by 5. And I don't know what 5, how big 5 is. So let's just make 5 be like this big. So that'll be there, this will be there, and essentially what you're going to end up with is this. Ish. There's your purple. The average went down by 5. The average was here. It's now here. There's down. That's a W, by the way. Sorry. Average went down by 5. Standard deviation. Question, what happened to the standard deviation? It's a bit of a trick question. What happened to the standard deviation? Say it, Trevor. It's exactly the same as it was. You were thinking that, Haley. I know you were. I know you were. It's hard to say that in a class like this, when I say, you're like, wait a minute. The data didn't change shape at all. Everything's the same distance that it was from the average. The average changed, right? The average changed. It went down 5 points. But everything else also went down 5 points. So the distances relative to that average didn't stretch like they did back in E9. In E9, everything was stretched twice as far away as it was, which means we're now more variable. Here, you took the entire data set and shoved it down 5. Nothing changed relative to the average, which means the standard deviation, whatever it was, is still the same as it was. Kind of cool. Which is a different answer than in central tendency, right? We drop the data points by 5, and the average actually goes down 5. You drop all the data points by 5, standard deviation stays exactly where it was. So That's another one of those reasons that standard deviation doesn't inherently make automatic sense to folks because of a question like that. So when somebody does look at test scores, for example, here's a classic example of that. You ever been in a class where they say, okay, class did crappy on the last exam, everybody had 15 points to it, okay? What does that do to the average? Go ahead, Armando. It increases it by 15 points. What's it do to standard deviation? Absolutely nothing. It doesn't change it at all. That's the problem I have with simply adding points. Because suppose the average in the class, as we saw on that one Math 95 exam, is a 75, but the standard deviation is like 25 points. If you just add 10 or whatever points to everybody's exam to bump them up, you haven't addressed the issue of the variation. Why is there plus or minus 25 points on an exam that's worth 100? Why should half of the points be plus or minus from the average? When I analyze this a lot when I look at your guys' exam results. I look at your class average, yes. I also look at your class median, and I look at your class standard deviation.